Well, hello everyone. All right, let's get into it, shall we? All right, so right now, we're going to be doing chapter 2.9. Usual rules apply. I'm going to read it, and then we're going to solve some questions. And looks like I'm pretty much set up and running good. Now, just keep in mind that we are doing odd questions, so same rules apply. You can get the book, it's in the video description. Download the book. It's free. It's in the Creative Commons. And the book is called Book of Proof, 3rd edition by Richard Hammock. All right, so here we go. All right, 2.9. Translating English to symbolic logic. In writing and reading proofs of theorems, we must always be alert to the logical structure and meanings of sentences. Sometimes it is necessary or helpful to parse them into expressions involving logic symbols. This may be done mentally or on scratch paper, or occasionally even explicitly within the body of a proof. The purpose of this section is to give you sufficient practice in translating English sentences into symbolic form so that you can better understand their logical structure. Here are some examples. Consider the mean value theorem from calculus. If f is continuous on the interval AB and differentiable on AB, so the first AB is closed, the second one is open, then there is a number C which contains A and B, for which the derivative of f of C is equal to the function of A, or f of B minus f of A, divided by B minus A. Alright, so let's do that. Let's just write the whole thing. Continuous. Alright, so, and this is how we're going to do this. Okay, so we have it's going to be a hard chapter. F is continuous on the closed of A and B, and F is differentiable this implies, that's the implies, keep that in mind. There exists C such that, or the C containing A and B, derivative of C is equal to, so my strategy for this is gonna be just try to work through as many of these as I can, because this is gonna be hard. Bring all this, but there's a form to this. Just have to be able to account for everything that's in the previous sentence. Okay, so let's just kind of look at it. All right. Make sure our parentheses line up. Right away, I'm seeing that I'm missing a parenthesis here. So this is one of the first things you do. You go in and check for your parentheses. It's one of the easiest mistakes to make. This is the shorter parenthesis. All right, so let's see here. F is continuous. We have to account for the fact this is continuous on the interval AB and differentiable. So we have F continuous on AB and F is differentiable on AB. Good. Which implies, now remember, if it's said then all numbers C containing AB, if it was like that, then we would have to use the universal, let's see here, the universal quantifier. Yeah, so in this case, we're using the existential quantifier right here, E. So because there's at least one, exists C, see here, number, read this one more time, which is a member of AB and derivative of C, and then you have the formula. All right, so pretty straightforward. Okay, let's continue. Okay. Consider Goldbach's conjecture from section 2.1. Every even integer greater than 2 is a sum of 2 primes. Okay, so basically, in regards to what that means is, so 2 doesn't count because 2 is the first prime. So we're going to say that every integer greater than 2 is a sum of 2 primes. Yeah, I'm sorry, I'm not an expert in Goldbach's conjecture. I guess it's technically 3. I wouldn't understand how they're going to process 3 in this case, because 3 would have to be a sum of 2 plus 1, but technically 1's not prime. I don't know. I'm not an expert in Goldbach's conjecture, but as you get bigger than that, right? Every number greater than 2, so for instance 4 is equal to 2 plus 2, so 5 is equal to 2 plus 3. These are primes, of course. 2 primes. It could repeat the same prime. 6 is equal to, I guess 5 plus 1, but again, 1's not a prime. Let's see here. Let me see here. Let me go back to section 2.1. Yeah, I don't see the conjecture here. Oh, here we go. Every even integer. Okay, that's what it was. I missed the word even. Okay, that makes a lot more sense. Every even integer is a sum of 2 primes. So, yeah, that makes a lot of sense. So, every even integer is a sum of 2 primes. So, we have 4 is equal to 2 plus 2. 6 is equal to 2 primes. 3 plus 3. 8 is equal to 5 plus 3. See here, 10 is equal to 5 plus 5. 12 is equal to 7 plus 5. Also, just 2 primes, right? Yeah, that's fine. 14, 7 plus 7. But I wonder if we can also do, yeah, also we can do 11 plus 3. That's also 2 primes. And what else is there? And there's also another thing. I forget what the other conjecture is, but basically, one other thing is, as you get in bigger numbers, the number of different ways that you can have the number of primes that can create that number It's prime factorization. There's other stuff that's similar to this, but it's a little different. And when you do prime factorization, you can have be like, and you can multiply them out. It'd be like 2 times 3 times 3 and so forth. Anyway, primes is very interesting stuff. I certainly find it interesting. But we're not going to mess around with that. Let's just get back on track. Okay. Okay, let's... A minute. Okay, here we go. So we're going to say this. This can be translated in the following ways, where P is a set of prime numbers. All right, let's establish that. P is and X, the set X. This is the large X. So 4, 6, 8. So that implies the dot, dot, dot. And once I establish a pattern, it'll carry on. Basically, this is the set of infinite set of even integers greater than 2. Okay? You can do that. You don't have to do anything fancy. You could just establish a pattern. I mean, for instance, let me show you just another example. This is much earlier stuff. We did this for a while, but we can do like, let's see here, 1, 4. Okay, that's going to be 7, 10, 13. I went a little longer so you can kind of see it, but basically, as you can see, I'm just adding 3. So yeah, and that pattern will go on forever. There are other ways, of course. This is like, I guess at a higher level, really, you're going to be more formalized. You're going to write this out rather than just kind of throwing down patterns, but we'll see. We want to be able to work both ways, right? So, we have this established now. What they're saying here... Okay, N containing the set X. And the set X is the set, this is the set of infinite number of even integers greater than 2. So, all right, so N contains that set, and that set contains those things. And now we can say here, this implies, if this exists, then this existence implies there exists P. P is going to be, now this is P, not our prime P, this is small p. This is P implies Q kind of a thing. P and Q. So, and now the type of relationship, so you could think of P and Q as statement 1, statement 2. You can have P, Q, R, S, T, whatever, it doesn't matter. They're just assignments that you can assign any statement to. Now, what's interesting is that the type of relationships that they have does matter, though. For instance, if it's an implication type of relationship, then it's not the same thing as, well, if it's an implication type of relationship, the truth table is going to be different than if it's just 2 different statements. An implication type of relationship is like cause and effect versus 2 statements where, you know, the type of truth they can have, and the relationship is dependent upon an and or an or. Anyway, we did all this. We covered all this. So this is the tail end of the chapter, but I'm just kind of throwing it back, just a quick refresher. All right, so now, okay, and these things contain, so our statements P and Q, for now we're just going to call them statements here. They contain the prime set, and so in this case, just to be clear, remember when I said that they can be statements? A statement can also be something like, this P is the list of all the primes, right? That's a statement, but it's also it contains something that you can work with, so to speak. So in that regard, it's not just saying like this represents a sunny day, but in a sense it is kind of like that. It carries values. So in this case, both P and Q are in some sense the same thing. They both are the list of the primes, but we need both of them because we need one of each. And the reason why we need one of each is because we can do this. Q. All right, so now if you look at this, N contains the set X of the infinite chain of even numbers that are greater than 2. And this existence, we're saying, implies that there exists the P and Q, which is basically each of which represents a prime set, and then P plus Q gives us the N. So yeah, so this right here, the second part, it kind of assigns value to what the N actually is. And the N is used to, because of those things that the N has, it kind of breaks down each of these things here in the X. So it's like a layer thing. So if you were to say, we're going to say P plus, I'm just going to do this myself. It's probably going to sound a little weird, but this is how we can stack it, I guess, like a cake, if you will. At its core, we have the P plus Q. Now again, this isn't division. I'm just creating a cake here, or like, this is probably better, more like a pyramid, right? P plus Q is over here. Those are primes. We use our primes, and those things assemble the N, and the N goes in, and they represent what the X is made out of. It's kind of like that. This is my own personal interpretation. So if it's not like strictly ballroom when it comes to math, it is what it is. It just sometimes I try to process things in ways that make sense to me, which, for good or ill, it is what it is, as long as I make the math work. And then, yeah, you don't need perfect understanding when this stuff. You just need a working knowledge, and you should be able to get the answers right. And then eventually, once you do enough of them, if there's something that you have a inaccurate, somewhat understanding, but still close enough to where you're getting the answers right, you'll eventually click and figure out what you understood differently. And it's usually some little nuance or applies to some special cases. So then you're like, okay, that makes sense. Like that. Okay. Another way to do this, another way we can do this. All of N containing the set X, there exists a P and Q containing primes such that N is equal to P plus Q. So that's another way we can do this. Yeah, this is going to be a hard chapter. Getting the answers right on this is going to be very hard, I think. Once we do enough of them, it won't be so bad, but I got a feeling that it's going to be like, oh, okay, that's how you do it kind of situation. Anyways, let's keep rolling along. These translations of Goldbach's conjecture illustrate an important point. The first has the basic structure of N containing X, which implies Q N. Okay, so and the second has a structure of, I'll put the second one back here. All n containing the set X Q n. Okay. Yeah, they have exactly the same meaning. This is significant. Every universally quantified statement, this is a universal quantifier. So every universally quantified statement means it starts with that. Can be expressed as a conditional statement. So here we go. So that's, yeah, we just covered that. Okay. And suppose, let's go to the next page here. And suppose X is a set and QX is a statement about X. So X is a set, and then Q of X is a statement about X. For each X containing the set. So in other words, for each member, this is a this is a membership. It is a member of that set. So basically we have here, this is a set, okay? So this is a statement about the items you could think of, or members, and this assigns membership to that set, the small x to the large set. So this tells us what those things actually are. The Q of X, it says something about those items that are located in the set. Okay, so now we have all X, they're members of the set X, QX. So that means that something about them that unifies them and makes them members of the set X, the items X. And that QX will tell us what that is. Another way to do it, we can say X has membership in the set X. X items have the membership in set X. And that implies, because they all have membership, right? There's got to be something that they all have in common, right? What is that something? It's the QX right there. That is the thing that gives them all membership. Okay, so now this fact is significant because so many theorems have the form of a conditional statement. The mean value theorem is an example. In proving a theorem, we have to think carefully about what it says. Sometimes the theorem will be expressed as a universally quantified statement, but it will be more convenient to think of it as a conditional statement. Understanding the above facts allows us to switch between the two forms. Oh, excellent. So this is what they're saying. This is universally quantified, and this is conditional, right? But that's fine. So all we can do is, if we take the universally quantified, we can drop the universal quantifier, throw the parenthesis around it, and set up the implication to that statement, because it says something about the membership. And yeah, so that's how it works. And when you're thinking about implications, right? So let's just say something to the effect that X, Q of X, let's just say this, all are negative. Okay, so now let's just go with, so basically what happens is whenever on an implication statement, if it's true that they're all negative, then it's true they're members of the set. And then, now this is not quite, now here we go. If they're not negative, then they're not part of the set. So that's also a true statement. So remember how when we have the false false on an implication statement, if we say if they're all positive and they're not part of the set, which is still a true statement, and remember how I said on implication, if it's a both are false, both P and Q are false, then it's fine, because what happens is then the statement still remains true as a whole, because like I said, if you think about that X, let's call this, okay, I'm going to go a little on a limb here. If I get this wrong, get it wrong, but let's just call this P, and then we're going to call this Q. Okay, so then P implies Q. The P statement here is all the X items that are members of the set X. And Q says here something about them, and that Q of X happens to be all or negative, for example. So if we were to draw our PQ, and P implies Q. Okay, so we're going to go true, true, false, false, true, false, true, false, true, true, false, true. Okay, so let's just review that. I just drew the truth table. Let's take the first line. We're going to say they are all members of the set X, these items, and they all happen to be negative. So that's a true statement. Next part, we're going to say if they're members of the set X, but they're not negative, they're positive, for example, then they're not in the set X. Again, this kind of works, but I'm probably doing it a little wrong. Someone will probably end up correcting me at this. But generally speaking, though, using the implication, like this, in other words, if they are not negative, they're positive numbers, but it would be false, meaning they wouldn't be part of that, because the Q doesn't happen. If they are not members of the set, but they're negative, I don't know. I have to play around with that. I'm not that good at actually doing conditional statements and using all of the truth tables. Again, I'm doing this to take this class. I generally understand it well enough to where I can make it work, but at this point, I'm kind of just going off track and just playing around with it, because that's how I learn, is just trying new things. So that's an idea, but let me go back to where we're at. Primarily what we were at is this. Let's see here. If we have this form, we could interchange it. And that, in some cases, like later on, we'll explicitly have examples where this makes sense to do this. Where we just take the statement all for all of X members contained in the set X. Q of X is the statement about them. And instead, we're just going to change this to the form X members in the set X implies that they all have the Q of X in common. All right, and for proofs, having those kind of flexibilities, it sounds a little weird and brain melty, but it's necessary. Yeah, sometimes it'll be very useful. Okay, so here we go. Understanding the above fact allows us to switch between the two forms. The section closes with some final points. In translating a statement, be attentive to its intended message. Don't jump into, for example, automatically replacing every and with an and sign or with an or sign. At least one of the integers x and y are even. So saying that at least one of the integers x and y are even. So I would probably say something like this: exists x comma y in the integer set, comma, at least once. So it would have to be x or y. X or y even like this. I would think it would be something like that. Okay, so yeah, at least that's how I would do it. Don't be led astray by the word and. The meaning of the statement is that one or both of the numbers is even, to be translated with or, not and. When we say x and y is even, it should be understood to be x or y, because it's the beginning is at least one of them, right? X is even, so we can say this. They wrote it much simpler. They said x is even or y is even. All right. Finally, the logical meaning of but can be captured by and. The sentence, the integer x is even, but the integer y is odd, is translated as x is even and y is odd. So this just gets flipped around, right? It's like that. That's for and. Okay. All right. So now, okay, we have exercises. Let me see here if the back's not working for now. Okay, let me just X out of this. File new. I think it crashed. Okay, 2.9. All right, translate each of the following sentences into symbolic logic. Okay, 1. If f is a polynomial, degree is greater than 2, comma, then its derivative is not constant. Okay. All right, so here we go. If f is a polynomial, so let's see here. So if we should translate as exists, there exists let's see here. Is a polynomial exists. Let's try. Weird, my backspace stopped working. Okay, there. That was really weird, and I have to paste it. So, let's do that. Exists f let's see here. I'm gonna make a okay f. Here we go. Probably like this. I'm going back to the previous page to try to use this as a model. Okay. Now, trying to get my pen to behave. Okay, I think it's working now. All right, let's see here. So we're gonna say F, and we're going to say F polynomial with degree, and we're going to say greater than 2. And then we're going to say greater than 2. Oh, wait. That's fine. That should be all right. F. And this is going to imply that so they're saying if it exists, then if P then Q, P implies Q. So this, what's it going to say? This, and then we're going to say then we're going to say, all right, let's try this. Exists the derivative of not. I'm totally gonna butcher this. I just know it. Okay. Let's see what they're gonna give us. Like I said, it's gonna get harder from here, but hey, we gotta get through it and learn it, you know? You learn through practice. Okay, checking the results. Okay. All right. Section. This is 2.9. Okay, translation. P and Q implies R. Okay, if F is a polynomial and its degree is greater than 2. So that's P. So F polynomial, we're going to say this is P, this is Q. So what they did was they wrote P and Q implies R. All right, and then we're going to say P is, actually, they were pretty simple. F is a polynomial, Q is a polynomial, F has a degree greater than 2, and R, the derivative of F is not constant. If I wanted to change this to the form that I was using, I would probably see here. I wouldn't say, we would not need the exists, I think, because it just implies the R. Okay, and then we're going to say this is how I believe it should be. F is polynomial and F degree is greater than 2. This implies that F is not constant. We have P, Q, and we have R. Okay, well, they're making progress. At least that's understandable to me. And hopefully it would be correct. At least it looks correct to me. The structure lines up. All right, now, next. Okay, let's see, we have 3. If x is prime, if you hear the word if, think if p then q. That means an implication. If, then, so we're going to say this is p, then root x is not rational. Let's find out. Okay, what did we say? If x is prime, okay, yeah. I'm just running root numbers right now. Well, yeah. That should I would think that would make a lot of sense, because you think about it, right? You're basically, what is square rooting? It's the inverse of multiplying an item by itself. So like, when we square root, we essentially want to know what are the two things that if we were to multiply them together would give us our original number. So if we square root 4, we're asking what two numbers can we multiply in order to get that number back. And the thing is, like, versus squaring is simple, because you take a number and you multiply it by itself, bam, you're done, right? Square rooting, you can't do that. You don't know what those two numbers are. You don't know, like, I could tell you that if root 2 is about 1.41, but it's not, because 0.4, let's just multiply 1.41 by itself. That gives me 1.9881. That's pretty close. The actual root 2 is 1.41421, etc. But essentially, those numbers, you don't actually know what they are. You just kind of have to. I mean, there's formulae. I believe it comes out to roughly, like, let me see here. So let's try here. Okay, so let's see here. If I'm just running some calculations. Anyway, the way it works with roots is there are ways you can kind of like guesstimate, and you'll be pretty close to what the root should be. And that will be actually covered more in my algebra and trigonometry book. There should be some examples of how to work out approximately what the root should be. But it's for our purposes, if you think about it, if you take a prime number, right, it's only multiplicable by 1 in itself. You can't crack a prime number in any even way, or I should say in any organized way. No matter how you break up that prime number, it's going to be a messy break. You're going to have, like, infinite repeating numbers in the decimals going back and forth, and so forth. So yeah, that's a way, if you think about it rationally, how to approach this issue. But yeah, I'm getting off topic. If x is prime, then root x is not a rational number. So we're going to say this is if p then q. P implies q. And we're going to say right, x is prime. And this implies root x is, or this implies not root x is rational. So notice I put the not in front of it there. Let me just move this down a little bit so you can I could have more room for it. You can do that. You can. It's just like a negative sign, essentially. I'm saying x is prime, which implies not root x is rational. All right, and that's, we have our p and q. All right, let's see what the book says. Okay. That's interesting. They actually did what I did. I wasn't expecting that. They did with the not. They wrote P implies not Q. Well, I guess it makes sense. It's instead of writing in here, like putting it is not rational, we took the not and we moved it out. Not Q. Okay. There. Okay. So yeah, basically now, and then yeah, P is x is prime and Q root x is a rational number. So yeah, it's just as I defined it. So specifically what they wrote is this, and then they went like this. P x is prime and Q root x. Remember, it's not rational, but we're saying here it is rational because we're going to not it. Okay. So that's good. Got that one. All right. Let's see here. We're going to go with 5. Okay, we have for every positive number e, there is a positive number. Oh, epsilon, there's a positive number delta. Beta, sorry, there's a positive number beta for which the absolute value of x minus a is less than beta, which implies, okay, just to formulate. Let me just write this out and then we're going to do that. For every positive number, we're going to say all. Okay. So we have for every positive number epsilon. So we're going to say down here we're going to start writing this out. Oh. What set does this belong to? The positive number, I guess, is contained in the reals. It doesn't say which, I guess. Yeah, we're using functions. Okay, we're going to see for all. I'll come back to that. Let's just write this out here. Epsilon there. It's just not working today. What's going on? trying to clear the history on this thing. I'm gonna have to. Okay, let me close this thing out and restart it. Try it one more time. Okay, I think I got it back to work here. Okay, so let's write this out again. For every positive number epsilon, there is a positive number. Yeah, this is beta. For, hang on, let me check my Greeks. No, I think it's delta. Beta should be like this. Let me check my Greeks. That's delta. Yeah, that I think a delta is this. But that's like a physics thing. That's often how you would do like for at least your intro physics. They would use delta like that, the large delta. But yeah, this is the small delta. Okay, so let's correct this real quick. All right. For every positive number epsilon, there is a positive number delta for which I'm trying to give it extra lines in case I'm going to write underneath them. For which x minus alpha is less than delta, implies the absolute value of f of x minus f of a is less than epsilon. This this has to do something with okay, I'm probably gonna sound like a total idiot, but I should know this. This has to do with the amount of change, I believe, and epsilon refers to the degree of the for which x minus a is less than delta implies f of x less than epsilon. I believe this has to do with E. What is it, 2.82? I believe, let me see here. The epsilon number, that's what it is. This is, I think this is what we're talking about here. And yeah, this is like, it's how much it can be off by, I believe. That's what it should be. Let's see, what's the value of E? Okay, yeah, it's a tiny number close to 0. This is, right. This is the epsilon delta definition of a limit. Okay, that's what's going on here. Yeah, basically, this has to do with, this gives us the limit of a function defined on a certain interval as x approaches some number x to 0, x sub 0. For every epsilon greater than 0, there is a delta, which is also greater than 0, so that for every x value, yeah. Too hard because the formula isn't intuitive at all. Okay. Okay. Says here, if you don't quite get what the formula is doing, don't be too hard on yourself. It's an initiation rite into the secret society of mathematical proof writers. Okay, cool. Yeah, okay, so this has to do with definition of limits. This is calculus. We're not going to worry about that. I will be doing the calculus book. I have 3 calculus books, so they're about 4 times more content than this book over the course of those. I'm looking at them right now. I mean, it's literally like a good, I don't know, like 3 or 4 inches of just solid, dense math of calculus that we're going to be doing. Yep, I have lots to look forward to. All right, yeah, let's get to this here. I've actually passed 2 of those books. One of them I have not passed the Calculus 3 book. So it's a benefit for me, but also even just a Calculus 1. Just because I passed something doesn't no way mean that I know what I'm talking about. It's you really have to sit right here and struggle with this material to really get anywhere. Simply just knowing it enough to be able to pass a test, and you'll forget it by the next week. It's just you really have to just make it a lifestyle commitment. Anyway, getting back to what we're doing here. So we have to take this statement. This is the epsilon delta definition of a limit, and we are going to be doing this. All right, so well, let's see what we can plug in here. For every positive number e, let's see here. Let's just say for a minute here. For all epsilon and there exists, a delta for all e exists delta, comma, and then we're gonna just drop this equation in here, x minus a, then delta, and we're gonna say this implies f of x minus f of a is less than epsilon. Okay, except now I just have to define them as positive and negative. That should pretty much work. I might need to throw some parentheses on this also here, let me think. Because we have an implication, I'll just put parentheses around that. All right, and then we're going to say for all e, we're going to say positive, so we're going to say greater than 0. Exists delta greater than 0. For all exists delta greater than 0. Yeah, I write chicken scratch. Just move things around a little bit here. Exists. Right there. Okay. Let's read it one more time. For every positive number e, so all epsilon greater than 0, there exists a positive delta greater than 0, yeah, for which we're going to say this. Okay. Yeah, I'm probably close, but I might be a little off because we defined the epsilon, and then, so the second part, for all, I'm gonna check the answer because I think I'm right, but I feel that I'm probably like 90% there. Let me just see where we're at here. Okay. All right. So they were more stringent than me. They decided to define the E in the reals, which, yeah, makes sense. So, and then I did not define that. So when they say for every positive number, we need to know what a number is, right? Does that include imaginary or surreal numbers? Since this is calculus, we are sticking, at least this definition of a limit of calculus is not really dealing with imaginary numbers, at least not at this level. So we're gonna, what they did was they defined in the real set. And then, so we're gonna have to tack on the all epsilon containing reals. Epsilon exists, so at least that's correct, comma. So that's where they threw the parenthesis on. So I was close. Yeah, no, I was very close. I'd even say about 90% is pretty accurate. They put the parenthesis right here. So they defined them and then they started dropping the formulas in. That's what they did. My definitions were a little loosey-goosey. I probably would have gotten most credit for this thing. Depends upon, how stringent the teacher would be feeling that day. But I did not define what a number is. It sounds trivial, but this is all about numbers, right? That's the name of the game. So let's just do this right. We're gonna redefine this. First, I'm gonna I need to move this down, and I'm just gonna write it the correct way. So we're gonna say all epsilon, they're members of the real set, epsilon greater than 0, and then we're gonna say exists delta members of the reals. I'm running out of room. And then we're going to say delta greater than 0. Okay. And let me see if that's correct. All epsilon members of the reals and epsilon greater than 0. And then we're defining the existed delta members of the reals. And the delta is also greater than 0. And then we have our first formula and we have the parenthesis around it, which implies the second formula. We have the parenthesis around that. Okay, good. So yeah, my parenthesis, I shouldn't have included the definitions inside the formulae. So I moved the parentheses in the correct spot, and then I defined what the numbers, which set they belong to. So yeah, not bad. All right. All things considered. Okay. All right, let's get back to it. So this was 5. Let's go to 7. All right. There exists a real number a for which a plus x is equal to x for every real number x. Well, yeah, it would have to be 0. If 0 plus anything gives you that number. So the answer is 0. Okay. Yeah, that's basically it. All right, now to write this, we're going to say exists a real number A. So we need to know what, there's only one number, right? Or a number, it could be a set of them, but really there's only one, that's 0. Exists A, which belongs in the reals, let's say all x belonging to the reals, and then we're going to say a plus x is equal to x, period. Okay, yeah, that's close. Let me just see here. Yeah, I'm going to go back to the previous chapter and look at the form of exists y for all. Okay, here we go. Page 55. Exists y, member of the reals, okay, for all of x members of the reals, and then we have the formula and we have a period. It looks right. I don't think I missed anything. Okay, let's find out. All right. All right, now. Exists a member of the reals, comma, for all of x member of the reals, comma, a plus x is equal to x. They didn't put the period on there. That's fine. In the example that I was using as a reference to check my work before submitting it, they used the period, and I don't know. It doesn't change anything. I mean, it's understood that that's a sentence, and you can put a period at the end of it. I guess you can get away with not putting a period or putting a period. But it's a kind of a thing. If it was a major issue, like your professor would quickly slap you down with anything that you're doing that you shouldn't be doing. Keep that in mind. All right. Okay. If x is a rational number, and x is not 0, then okay. So this is P implies Q. If then means X is, or the first statement implies the second. Okay, here we go. Then tan X all right. Tangent X, okay, is not a rational number. If X is a rational number, okay, so rational could be written as a fraction, and X is not equal to 0, then tan X is not a rational number. Taking the tangent of the X, and the tangent essentially is represents sine over cosine. Okay, yeah, so this is trigonometry. I'll leave that for when we're doing the trigonometry book. I don't want to meander in this too much. I'm already working on that book So I haven't gotten into it very far because I just want to drive through chapter 3. I want to go wild here, get all that done. And then when we start hitting, see what happens is the book is divided into 2 parts. The first 110 pages, they just melt your brain with all the stuff that we need to know how to do proofs. And a lot of it is just like stuff that you're going to be working, pigeonhole principle, combinatorial proofs. That stuff's awesome. Various ways of counting. So yeah, all of that is the first 110 pages. We're only halfway there. And then part 2 is when we start doing the conditional statements. And I don't know if there's a part 3, but essentially it's that they start to do the actual proofs in the once we hit page 111. So yeah. By the way, technically speaking, if you want to be super technical, I've shown you guys probably a dozen proofs by now. Basically, anytime that I proved something directly, it's called a direct proof, just so you know. Like, anytime I'm like, oh, yeah, you can do that, and I just show you how you do that. Anytime I say, well, let's show the one example where it breaks out of the set or whatever. So, yeah, like, that kind of stuff is a direct proof. All right, so now let's do this right here. If x is a rational number and x is not... Wait a minute here. I wrote that wrong. Okay, hang on. Right, that's how I should be writing it. The way I wrote it is just that x is an empty set, or I don't have to think of it as empty set. You can technically write zeros that way too. Not equal to 0. Okay. Okay. Right. Okay. Well, let's do that. Here we go. If x is a rational number. Okay, so we're gonna say. So this is P and Q. We're gonna say this is P implies Q. We're gonna say P x is a member of. This is a different kind of Q. This is the set Q, and that it represents. This represents the rational set. Which, by the way, what does the Q actually stand for? Let me tell you real fast here. Okay, let's see what the Q stands for. It's a quotient, I guess. Okay. I guess that makes sense. Terminology. Yeah, ratio of two integers. Okay. Yeah, Q, we think of it as quotient. So, and these are rationals. So, here we go. And of course, quotient is a fraction. Or ratio. So basically, yeah, anything can be written as a fraction or ratio is a quotient, and that is the rational number set, which again, technically, you can have whole numbers in it too. Like you can have 2 over 2. That's still 1, right? But anyway, so P implies Q. This is a different, X is a member of the quotients or rationals, different kind of Q. Don't get these two confused. And then we're going to say, comma, x is not 0. Okay, and then we're going to say, oh, okay. No. This P implies not Q. This is what we're going to do. We're going to say not Q. And our Q is not, we're going to say tan is not tan is a member of the quotient. That's what we're going to do that. Tan X. Okay, I'm going to rewrite that. It's a little messy. We're going to say not, this is the not symbol right there, not tan X is a member of the quotient set. Notice these Q's are different Q's. They're not the same thing. They're not the same thing. Okay? So in this case, this is a logic Q. It's like P, Q, R, they're logic. And they are statement assigners, essentially. You could assign a statement to them, and that's what they represent now. This Q right here is a type of set. And so we have, if X is a rational number, so it's part of the quotient set, and X is not 0, so we're going to say P, X is a member. Oh, okay, hang on. There's one other mistake I made. I'm doing a not here. See how I put the not? That shouldn't be there. All right. This is how it should read. Because if I thought about it, otherwise, this not right here, that not, would have double knotted it if I had a not right there. So I took it out. Yeah, double check your work twice, submit it once. So we're going to say P implies not Q. P states X, and this is just a small x, even though I kind of drew it big. This isn't like a set X, it's just like a regular old X, meaning that it represents like items and numbers. X is members of the rational set, so it's just a set of the rational numbers, except they're not 0. You can't have 0 in the set. And Q, the statement is that tan X is a member of the rational set. But our statement reads, if X is a rational number and X is not 0, then tan X is not a rational number. So we're going to say P implies not Q. All right, and let's take a look. If X and X, translation, X is a member of Q and X is not 0, which implies tan X is not does not contain. Now, I wrote it differently, but it's the same thing. If we were to consider what they did, I essentially went off what they did in number 3. If X is prime, then X root X is not a rational number. Now, it's also an if-then statement. It's also an implication statement, and there's also a negation in this case. Only they did not go with a negation. They simply wrote it this way, which same thing. This means exactly the same thing. So I have the negation on the outside. They put it on the inside, and they're doing that so that we are comfortable reading both ways. So you can go P implies Q. We're going to say P. Now they're going to write it differently. They're going to say, see how they wrote it. But again, my answer was technically still correct. And they're going to say, now I wrote it as separating the P's and the Q's out, like they did in question 3. They just went with parentheses. That's fine. So they wrote a more technical version. We're going to say X contains the quotient sets and X is not 0. Okay. And this implies tan X is not part of the quotient set. Okay, so that's how they did that. Now, if you're going to write it like that, you don't really need this part here. That is if you're going to break it down like this. So, yeah, they didn't put that there, except they, yeah, you don't need to write it like that. I'm just going to take this out. I was just writing it to explain the difference. The knot, here, I'm going to finish to explain the difference. The knot, this part right here, was the knot right there, okay? I took it out, they put it in there, which is totally fine. I should have gotten full credit for this. I don't see why I wouldn't have. Obviously, I'm not a teacher. I can't say anything definitively, but as I understand it, I wrote it exactly as they did. And yeah, it's fine. Same result. Keep in mind that even, like there's going to be variations of language and stuff and structure. But yeah, that's fine. Okay, let's continue. So long as the meaning, okay, the key here is the meaning. There is a province, there's a providence, as in like a spiritual thing or a god, or something that's like a cosmic thing, if you will, a cosmic intelligence. There's a providence that protects idiots, drunkards, children, and the United States of America. Otto von Bismarck. Yeah, no, he's absolutely right. Yeah, that's it's like they say, it's very hard to kill stupid. That's what the American version of that statement would be. Not I'm saying the United States of America is stupid. I'm just saying that generally speaking, the first three items, the idiots, drunkards, and children, are like this. In this case, refers not as in like necessarily. I'm digging myself a big hole here, ain't I? Let's keep digging. All right, but anyway, we're gonna take this quote by Otto von Bismarck, and we are gonna write it out here. He would be so canceled today. Okay. Okay, if you don't know who Bismarck was, he is the guy that formed I think the Second Reich. I believe, because, let me see here. He's the guy of blood and iron. Otto von Bismarck. I'll tell you real quick the background to him. German statesman and diplomat. Oh, he reunified Germany, I believe. And that, let's see here. He was Prussian minister. He masterminded the unification of Germany and served as a chancellor of the German Empire. So this would have been the Second Reich, I believe. Yeah, okay, well anyway, German politics aside, let's finish this thing here. Protects idiots. Drunkards. Children. Okay, so they didn't use comma after children. I guess they're using the Chicago form of a writing style, the Chicago writing style. I believe they don't use a comma after. When you have a list, only the Chicago style, that the last two items aren't separated. They're just by an and. Whereas the other styles they all have the commas. No lie, though, America has the best geography in the world, at least with current technology. We are protected with 2 oceans. We have every conceivable type of climate. We have great natural resources. We are self-sufficient. We have plenty of ports. So yeah, America's blessing is definitely... This is the most incredible, the most blessed geography in the whole of the earth. This is not a controversy of any kind. I mean, if you look at it, it really is. I mean, now granted, that's also a function of whatever technology you use. I mean, if you're dropping rods from God, that's a technical term that refers to dropping a dense ore, like a rod in the form of a dense ore, and essentially like a gravity weapon where you would drop it from a satellite. Think of it as dropping a meteor onto your opponents, like that would change things. Or if we had, like, I don't know, I guess space elevators or something, where how we moved around on the Earth wouldn't be really important. Instead, everything would, like, our heavy industry would be up in space. That would change things a lot. But the seas and the skies are incredibly important. And I'm getting off topic. Anyway, there's a providence that protects idiots. There, protects idiots, drunkards, children, and the United States of America. Otto von Bismarck. Okay, so we have a list. Ooh, how are we gonna do this? So okay, this is, I'm gonna have to think about this here for a minute. Okay. So, in other words, there's at least one providence, not all of the providences. You could say that, like, for instance, there's what, like 5,000 different deities, but at least one of them is the deity that protects the United States. So we're gonna say exists, and we're gonna say let's just assign here. Okay, providence that protects. Is this providence? We can just write it as there exists a providence and protects all idiots, drunkards, children, and the United States. And then that if, hang on a second, exists a providence that protects, and then, well, how do we even describe the word protects here? Oh no, how about there is a province is one, that's P, and that protects idiots, drunkards, and children in the United States. That can be Q. Maybe that protects idiots, drunkards, children. If P, then Q. Let's see here. P implies Q. I guess that's how we would be. There is a providence. This P, comma. Okay, let's take our oh, we have a set here. This is a set. Okay. We're gonna use fact 2.2 on page 58. Okay, for all of members X contained in X, comma, as we're gonna say Q is X, and we're gonna say X is we're gonna say all drunkards hang on. Okay, all... Okay, let me think about this for a minute here. If we say P implies Q... No, hang on a minute. Q is... X is a set and Q of X is a statement about each. Okay, let's say... This is... I'm getting somewhere now. Q of X... Q of X is provenance that protects, okay? And, X is a set. And we're going to say X, this is big X. So we're going to say this, idiots, drunkards, okay. Idiots, drunkards, and the USA, children in the USA. And we're going to say this. For all... Yeah, we're going to say that. We're just going to try that. We're going to say Q is the providence that protects. It is the thing that that does stuff. That is the thing that's like the blanket. It is what makes them the members of the set. What do idiots, drunkards, children, and the US have in common? Not a rhetorical question. But in this case, they're all members of a set. What is the uniting thing with them? They all have a providence that protects them. So that blanket that engulfs them is going to be the Q of X, right? So then we're going to say for all members of this set, and then X is a set. So the only thing is that I define the set. How about X? The set. Okay, suppose X is a set, and this is the members of the set X. Except I wonder how I want to define this. Okay. For all X. Do I need to define the set, or do I need to define the X? Let's see here. I'm just going to define it as a set. Again, I feel like I'm like 95% there, but I can be way wrong. Let's find out. Okay, how did they do this? So they have several, one of which, okay, P of X is a province. So I said Q of X, that's fine. Let S be the open sentence, S, X of Y, X protects Y. All right, here we go. We're gonna just do it their way here. Let's see. P of X Whenever you use the word let, try to write that down because we're assigning something. Let S be open. S of X of S X comma Y such that X protects Y. We're going to say exists X, which is a province, for all Y. And X protects Y. So then, and then we're going to say Y containing Y are a member of the R. Okay, R, I see that R is a union set. Okay, I'm just going to finish writing this first. I forgot to write the union set. And S of X and Y. Okay, so basically R is the union set of idiots, drunkards, children. So R is going to be this right here. Okay. So R is the union set and it contains all those things. So then we have exists X. X is a providence for all of Y that are members of R. For Y are the listed items, and R is union set. Y are the individual items in it. S is an open sentence where X protects Y. So then P of X is the province that protects, and it exists as S comma X of Y. I feel that like the way I did it is a little more straightforward. I mean, theirs is more bulletproof, I'd say, but I don't know if I'm necessarily wrong in how I did it. I still feel that I did a pretty decent job of putting it down for something that wasn't really what this formal language was designed for. For all of X being members of X, so so let's look what they have, right? I said for all of X. So for this case, they have all of Y members of R. So and I had all of X being members of the set X. So let's just look at comparisons and see where we match up. I have this and that. Those two are the same, essentially. And then we have P of X, and then I just assigned the Q of X. Now, for me, is that they broke it up into two parts. The P of X is a province, and X protects Y. For me, where my flaw here is, it says it's a province that protects. I think it could still work, but in this case, they specify what it protects. So I could have put in another Q and R, for instance, R of X. And again, it would define where did S of X and Y. I can do R of X and Y and unify that way. And then we would probably, the first part, there is a province. This way exists X. Oh boy. Whew. They really wanted to mess with us on this one. Okay. That's another great benefit. If you get really good at math, I mean really, really good at math, you could write your own textbook and then mess with other college students, you know? Anyway, everything is funny as long as it's happening to somebody else. Will Rogers. Okay, another one of those funny ones. Funny man. Let's do this. Okay. Okay, so everything we're gonna say here, I'm just gonna try to slap this down and then try to clean up a little bit. All of funny, we're gonna say P of X, say all is funny. Actually, hold on a minute. And then we have if else, as long as, if and only if. So an implication. All right, so we're going to say if P then Q. Happening to not someone else. Everything is funny. Exists E. Or if P not Q. I might have to define myself in this case. Because this is said from one's perspective. Okay, how about let's see here. X is the observer. What is everything? Everything that is funny. Union set of everything that is funny and everything that is happening. Okay, everything is funny. Exists funny. Everything is funny. So all P of X is funny. All is funny. All funny. Q of X, someone else. Okay, I'm just giving assignments. Funny, someone else. All P of X is funny. Now I have to mention happening. P, happening. Q, someone else equals funny. If as long as that's if and only if. Okay. So here's what we're going to do. That's, I wrote it too shortly. As long as it's if and only if. I'm just going to try to copy some of this. Someone else. Okay. Now we're going to say let's see, all P of X everything happening about, okay. P, everything happening, P of X is everything happening. Q of X, we don't even have to assign a specific thing. We're just going to say P and Q here. I'm just going to try to keep this as simple as possible. Might be a little bare bonesy, but it'll work, I think. P, Q. P is everything happening, and Q... No, we still need P of X. P of X is things that happen, I guess. Okay, I think I got it. P of X, things that happen. No. This might work. Everything that happens, and then I'm going to say this. Everything. Let's get rid of the everything. So P of X, things that happen. Q of X, things that happen to someone else. Okay, so and we're gonna say if we're gonna say P of X and Q of X imply R of X R. We're going to say all P and all Q imply R of X. So all P and all Q, all things that happen and all things that happen to someone else are, if they are members of the set, in other words, if they are, if things happen and they happen to someone else, then it implies it'll be funny. That's how I'm going with it. 13. Let's see it. And let's see here. They wrote all of x. So I was pretty close. All they did was they defined the x outside. So what I should have done is, so here's what they did. I don't know. I might have gotten away with doing that, except it's just to follow along. I was pretty close though. We're gonna say all of x. Okay, let's see here. And then they said they did M, S, it implies F. So yeah, you got that. And yeah, got the parenthesis. I got the implication right. Let's see here. Let me make sure. F of x is funny. In this case, they use the word things, but x equals things. We're gonna say need to define x. X is things. Okay. M is so the difference is I defined Q of x as things that happen to someone else. They defined it as M of x. Again, the M doesn't matter. They defined their version of Q of x as x is happening to me, or things. And by defining x here, I can take the word things out now. All right, so we're going to say x. So I'm just cleaning up. Like I said, I would have gotten majority credit for that. The only thing is I didn't define the x, which I just kind of defined it in there. I mean, maybe I've gotten like close to full credit on that, I think. Anyway, so we have M is x happening to me. I'm going to keep my version of it where x happened to someone else. S of x is happening to someone. And I just define it things that happen. The implication here is to someone. So I didn't write that part out, but implying things that happen, yes, we can add to someone. I see what they did. Yeah, well, this is where the not is actually a good thing, because I have they're too similar. X that happened to someone, X that happened to someone else. That I need to negate that. This is where they did that. We're gonna negate the Q. So the Q is gonna be to me. So again, I'm going off their solution. I'm fixing my thing to make it. So Q, we're gonna say that happened to me, and P is gonna be just someone. Now in this case, it could be me, it could be someone else. So the P of x could be me, but by combining that with not me, we can't be me and not me. That's a false statement. That is, if you look at the truth table, it wouldn't work. So what would happen is the P has to be, they both, because on an and, they both have to be true, right? Okay, Q, P. So true, and true, false, true, false, false. Okay, if they're both true on an and, it's true. If one is true, it's false. The other's true, it's false. Both true, that's false. So that's the P and Q. It only works if they're both true. So in that case, yeah, it's a true statement, and we just negate that. We say not. So in this case, we're negating the Q right there. So we take the Q of x that happened to me. We're going to say not happened to me, and that implies R of x. R of x is funny things. Yeah. So yeah, that's the corrected version of it. There you have it. So that was I found this one a little easier than the previous one with the list and creating the, I mean, you got to do all of them though. It's there's no getting around it. This stuff's hard, and but it's not like not doable. You just have to keep plugging away at it. There's more negating statements, and that's going to be 2.10. Just going to look at that real quick here. What do we have here? Okay, so that's probably another 2... How many hours was it today? Yeah, this stream's about 2 hours long. All right, it's already past midnight, so I have to go to work first thing in the morning. So, like every day, of course. But, yeah, and I also have to teach afterwards. So tomorrow night, when I come back from coaching, I guess, then I will hit this again. We're gonna try to finish out. Being optimistic here, but we just finished 2.9, which is pretty impressive. We get through 2.10, and then 2.11, we just read through that, and 2.12 is just a note. So 2 to 3 hours, we should be in chapter 3. In other words, 2 to 3 hours more of streaming, and then we learn how to count. Hey, that's always great. I'm looking forward to the day when I know how to count. Oh my goodness, we have so much material to read through. Yeah, we're gonna read through like 10 pages before we even get to the sections. Right, the first section appears to be just reading material. Yeah, and then this isn't too bad though. Then it picks it up. Yeah, but good. I can't wait till we get through to page 75 or something. Get through the first section of counting. I think it won't be bad, and I'm really looking forward to this. It's gonna be fun. I enjoy every part of it though, so I'm not trying to rush through this part. As you can see, I meander all the time. This is the only way that I'm ever gonna truly master this stuff. At the end of the day, this is me studying. This is my study time. I gotta keep it, I have to take my time and really just dive deep and try to learn it instead of blow through it. Otherwise, it just doesn't stick. I have to really develop it so that I have a understanding of it, because rote memorization will only take you so far. You just, certain things you need rote memorization for, but understanding is so much more powerful. Like, I can't even begin to tell you. All right, well, it has been fun.